Welcome back to the lab, welcome back to EE for Everyone. Today we're going to wrap up this DMX series, but first, a quick pause to acknowledge the elephant in the room. This series hasn't been moving very fast. We've been taking a few moments to get into some of our good old habits, actually trying to explain things in detail. And it's been great. And also, I'm kind of done with this project. Not for any particular reason, just kind of all of it together. I mean, I designed this board more than 8 months ago. I think it's time for something new. Before that though, let's give this project a proper send-off. Let's finish telling the story of this project by discussing some LED driver circuits that I considered. Let's highlight the design that didn't make any sense but got built anyway. Let's visit the design that mostly worked, except for those 2 times when it caught on fire. And let's discuss the final touches that are required to prevent these boards from going nuclear in the future. I suppose that if we're going to talk about all that in one video, we may as well start at the very beginning. Our goal is to control analog LED strips using DMX without introducing flicker or flashing artifacts when viewed by a camera. We've discussed many elements of this project in detail before, including the DMX protocol, this aliasing effect. That's all captured in our previous videos, so there's some links in the description for that. For today though, let's move forward and discuss a couple theoretical concept circuits that attempt to drive an LED without introducing flicker. Let's not let physics contain our dreams just yet. First idea, the sort of buck converter. Next, a marginally stable linear regulator, and also faster PWM. Faster PWM is a really tricky concept because we need to understand how fast is faster enough to solve our problem. 500 Hz PWM is easy to achieve. 1 megahertz? Not as easy. So let's break this camera LED system down into its core concept to find our answer. At its core, the camera is just a sensor that samples a signal, which in this case is light. The general rule of thumb is that to successfully capture a signal, you need to sample it twice. To capture a light flashing at 20 Hz, that would mean the camera must sample that light at no less than 40 Hz or 40 frames per second. This comes from the Nyquist-Shannon sampling theorem, which unfortunately has no bearing on what we're trying to do today. We want the opposite. We want the camera to completely miss the fact that our LEDs are flashing. We don't want visible artifacts to show up in our video feed. And I don't think there's a frequency above the sample rate that guarantees no aliasing artifacts. Setting our bar a little lower then, what if we don't try to completely eliminate aliasing, but we do try to make it less noticeable? In that case, pushing our frequency faster should be okay eventually. If the LED were to flash twice during 1 frame sampling interval, we should capture at least 1 of those flashes in each frame. Usually we'll get 2, but sometimes we might only see 1 or 1.5, something less than 2, just because these frequencies aren't perfectly synchronized. So that would mean that the LED strip may appear more or less bright in a given frame, but it should never appear off. So that should lead to a much less noticeable aliasing effect. And if we were to take that PWM frequency and push it even faster with maybe 4 or 5 or 10 flashes during each camera sampling interval, that should really smooth this out and make the captured light a lot more consistent frame to frame despite the aliasing effects. So that might get this to something manageable for video content. Of course, that sounds great. But we still haven't found that magic frequency, that minimum frequency that we expect to solve this problem. We're just walking down a path towards that solution, so let's continue. A camera doesn't sample for 1/60th of a second when capturing 60 frame per second content. We don't get that whole 16 milliseconds. Assuming the exposure is about 1/4 of that frame time, which feels like a lot, but I found some stuff on the internet that seemed to back that up, it'd leave us about 4 milliseconds. With that in mind, each PWM interval would need to be half of that, or 2 milliseconds, about 500 Hz. That math is awful. It's napkin math at best because different video exposure settings or different cameras will change the exposure time at a given frame rate. So let's assume the average camera will adjust that frame time by no more than 50%. That would give a minimum PWM target frequency of around 1000 Hz, 1 kHz for 60 frame per second video. 1 kHz makes the PWM approach seem more palatable, though that does put it in the audible range, which sucks. Audible frequencies in electronics leads to things like coil whine, and generally it's no good. I don't really want that. Okay, so 1 kHz no good. What if we push above 20 kHz so it's no longer audible? Well, that's also not great, because now we'll need to start thinking about switching losses in the MOSFETs that are driving the LED strips. And gate drive currents, it'll get a little more complicated if we go much faster than that. Not to mention finding a PWM controller that's both cheap and can handle those higher frequencies. So maybe some sort of system that would have the ability to choose a frequency between 50 kHz and 1 kHz may be ideal. That way we could play with the different frequencies and weigh trade-offs with some measurements down the road. To make that long story a bit shorter, 1 kHz is the target minimum frequency for now. On to the next concept. My almost buck converter design is kind of clever in principle, though it's not groundbreaking. Color accuracy should be pretty good, similar to the PWM approach, because we're driving each string of LEDs with a duty cycle. In practice, this fell apart a bit because keeping the minimum current above 0 required a 1.2 megahertz switching frequency and a 100 microhenry inductor. Wow! Multiply a 1.2 megahertz PWM controller and that inductor cost by 4, one for each color, and this idea is more expensive than buying the off-the-shelf solution. Not to mention, if we wanted to switch at 1.2 megahertz, we could just drive the PWM at that and it would be fine. Honestly, any discrete LED driver IC multiplied by 4 is probably going to be more expensive than we can stomach. Again, there are off-the-shelf solutions that do solve this problem, but they have the benefit of volume discounts, and we're building like 3. So we don't get that luxury. So it's kind of a shame, because this would work, but not for us with what we're trying to do today. This, of course, brings us to the unstable linear regulator. A linear regulator built using an op-amp and a series pass P-channel MOSFET or a PNP transistor is pretty common. A textbook example of a simplified LDO, in fact. It's fairly easy to design, inherently stable, and it works very well with a decent reference. Unfortunately, the LED strips we're using have a common anode and separate cathodes, which is pretty common. The direction of current flow for the standard LDO that we just described doesn't work here. We need a current shunt rather than a current source. I wish I could remember all the iterations of this concept that I tried in LT-Spice with different FETs, P-channel, N-channel, NPN, PNP, different op-amp configurations, single supply, dual supply, but we ended up with something that mostly worked, though it's barely stable. I'm reasonably sure that a part of this instability comes from the high gain of a BJT when it's driven with voltage. What I mean is the op-amp outputs voltage, which starts driving a lot of current through the base of the BJT, which leads to even more current through the LED strips, which changes the voltage rapidly at the collector of the NPN transistor. Adding a 500 ohm base resistor and a 100 picofarad feed-forward capacitor seems to keep the simulation happy, but only just barely. The main problem with this solution is, if I take a moment to look deep inside myself, get scared, run away, finish prepping this video, and then continue, I know I can do better. This is far from my best work, and I'd argue that it's in fact some of my worst. I had the idea, I did a quick simulation, I realized it didn't work, and I built it anyway. I could continue listing the many different reasons why this board is a bad idea and become my biggest critic, but thankfully I've already taken care of that in our live stream. Somewhere vaguely halfway through our live stream, I listed all those reasons why I hate this design. So instead, I'll do what we all need to do sometimes. I'll just dust myself off, admit I did something silly, and move on. Moving on then. After losing round 1, I had a half-baked idea in a way that most hardware nerds can probably relate to. Isn't there some kind of PWM chip that people use with Arduinos all the time? I swear I remember something. Why, yes! Yes, there is. It's the PCA 9685. It supports a maximum PWM frequency of 1.6 kilohertz, which is barely faster than our napkin math recommended, so I guess it's good that it's faster. I'm all for napkin math, and there are far too many bold assumptions about how every digital camera operates in there to accept 60% margin on the result. Maybe 100% margin, but yeah, that's not enough for the legitimacy of this math. At any rate, I did that anyways, and it seems to work, at least for a 60 Hz camera system. Maybe I just got lucky, and that camera had a particularly long sampling time, or frame time, but yeah, I'm glad it worked. Of course, this is a balance between cost, complexity, and just buying the thing off the shelf. So it was basically we'll try this, if it doesn't work, we'll just buy it. That's kind of where we landed. So some of you might be thinking, but EE for everyone, how can you say something like this works when the board isn't even populated? Well, that, dear viewer, is because I'm showing you the boards that didn't light on fire to hide my shame. Let me introduce you to exhibits A and B, which have set themselves on fire. Note to self, UL94V0 rated PCBs next time. The rest of these boards may or may not still be happily doing their job, creating a flicker-free light being viewed by a camera. The story behind why these failures occurred is actually pretty simple. Everything was fine until someone was rearranging some electronics and both catastrophically failed. In my defense, I'm about 98% sure that the boards were being rewired hot, as in they were not turned off while modifying the circuit, which is a terrible idea. In fact, I can pretty clearly see that 2 of these have failed with the output transistors. There's very likely a short in this cable to 12 volts, which then blew it up. But in their defense, I totally forgot to add a TVS and a fuse leading from the power supply, this 12 volt input, to the 5 volt buck converter, which is the component that became a crater in this board. In my hurry, I somehow remembered to add fuses for the LED strips, while forgetting to add a fuse between that 500 watt 12 volt power supply and the onboard circuitry. I love 500 watts being pumped into a silicon die as much as the next guy. But this is a perfect example of a circuit that could easily have a fuse without harming its function, that should have a fuse and that would have been saved by the fuse. This board only uses a few tens of milliamps. A fuse rated for even 200 milliamps would have tons of margin and would have totally prevented this catastrophic failure. With a fuse and a TVS, these boards might have even survived, living to fight another day without these critical protective components. Now, I'm pretty sure that all the 5 volt circuitry got nuked with 12 volts as the regulator went out, which sadness, but thankfully replacing the 0 ohm resistor with a PTC or PCBA mount fuse will do fine, just fine. I need to add a TVS in parallel with one of our input capacitors on the buck. No board spin will be required to add that fuse in series and the TVS in parallel, which is great because then they can keep using the boards without worrying about them lighting on fire. Getting out of the technical world for just a second, all of the problems we just discussed in both of these boards are a direct result of feeling pressure to deliver a solution right now. I cut some corners that shouldn't ever be cut and ended up spending more time and money fixing it because of that foolishness. It's one of those things that just shouldn't happen, and yet it is so hard to avoid. This project has become a great example of how not to do a project, and a perfect cautionary tale that will hopefully help you to say, we shouldn't go that fast, let's do this right and do it once. This failure wasn't a big deal. Nobody got hurt, nothing was damaged outside of these boards, and it's fixed now. When the same pressure gets applied to design teams building planes, rockets, automobiles, or infrastructure, that's when it's an engineer's duty to say no, even if it gets you fired. It can be scary sometimes, but you gotta think about how it might be used or misused. Coming up next, we'll be starting a new project that I am very excited about. It's going to be a new challenge, a different kind of challenge, and I can't wait to share it with you. As always, I'd like to give a special thank you to our channel members on Patreon and YouTube. I really appreciate the extra step you've taken to support us directly, making cool projects like this one possible. I'd also like to thank you all for your support through viewership, comments, and sharing what we do with others. Those who choose to watch ads and those who are subscribed. It has been awesome and humbling to watch this EE for Everyone community grow, and that just can't happen without you. So thank you. Most of all, I hope that you learned something great today, and I hope to see you again soon. Thanks for watching EE for Everyone, and thank you for staying till the end. Bye!